All right, let's finish up this experiment. We are talking about experiment 10 for Chem 101 at Cal State University Northridge for the lab. And for part 2 of the laboratory exercises, it's saying these will be performed in groups in class, but we're not in class and we're not in groups. So you can consider me your team member. So what we want to do is we want to answer question 2. If xenon tetrafluoride is non-polar, what must be the shape of this molecule? Explain. So let's go ahead and grab the xenon atom, and let's go ahead and zoom in a little bit, field of view, and then let's grab a fluorine atom, and let's add it to our xenon central atom. Now let's take a stock of the electrons. Xenon is a noble gas. It has 8 valence electrons. Fluorine is a halogen. It has 7 valence electrons. There are 4 of them. So 4 times 7 is 28. And 28 plus 8 is 36 electrons. So we need to be showing 36 electrons on our structure here. So let me grab the template that has the lone pair electrons. And let me just add these to the atoms that are not our central atom. Let me grab the other diagonal electrons. Add these central atom. So let's count. How many electrons are we showing right now? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We're only showing 32 electrons. So we need to show 36 electrons. So let's go ahead and add 2 more lone pairs on our central atom. And we can just put them wherever we like. Xenon is in row 3 or below, so it is allowed to have an expanded octet. So this is fine. Fluorine is not in row 3 or below, so we can't put the extra electrons on the fluorine. And now we can think about what would be the shape of this molecule. So if we go to select our molecule and we go to clean the structure, it's going to make all the bonds the same length, and it's going to kind of square up the structure so it looks prettier. And then we can also optimize the structure for 3D. So if we go to 3D structure optimization, and then we copy to 3D viewer, we can take a look at what the software thinks this shape will be. Now, I disagree with this shape, and maybe what we need to do is, you see that there's a -4 charge here, and that is not the case. We want to go ahead and remove that. So maybe now, if we try to copy this to the 3D viewer, we'll still 3D optimization. Still not giving the right shape. So it tells us xenon tetrafluoride is nonpolar. What must be the shape of this molecule? Well, okay, so let's go back and let's think about the how do we tell if a molecule is polar? We have to evaluate whether the molecule has polar bonds. So we have to look at the electronegativity values of fluorine and xenon and calculate the electronegativity difference between these two elements. So let's do that next. Looking in the lab manual about the electronegativities in figure 10.1, we see that xenon has the electronegativity value of 2.6, and fluorine has the electronegativity value of 4.0, and the electronegativity difference is 1.4. So we would say this is a polar bond. Now, in order to think about what would be the shape of this molecule, we need to think about how many domains we're seeing here. So on the central atom, it has 6 domains. That would be 2 lone pairs and 4 bonds or bonding pairs. And the name of that shape for the electron pair geometry is going to be called octahedral. That shape for the molecular. If we have 6 domains and we have 2 of them are lone pairs, the name of that shape is square planar. And that's why I disagree with the shape that is being proposed by this 3D optimization. It's not taking into account these 2 lone pairs. So I would have to share with you the model, but I don't have it built right here. So I have to make a separate video, a molecular model of that. But remember that your octahedral geometry is all 90-degree bond angles. And since I'm on Zoom, I guess I can draw it in my drawing. So if we had our octahedral shape, what would happen is the lone pairs are going to go as far apart as they can from each other. So we have our lone pairs, let's say 180 degrees from each other. And then we would have our fluorines bonded in this area here in the center. And we would call this square planar, because what you have here is you have a rectangular arrangement, or it's actually a square, not a rectangle, it's a square. It looks like kind of a parallelogram because I'm trying to represent its 3-dimensionality. But that would be the square planar shape, what it would look like. And the 2 lone pairs would be as far apart as they could from each other, which would be 180 degrees. So the question in the lab manual was asking, if this is a nonpolar molecule, what is the shape of the molecule, and explain. So what I would write for that would be, this is octahedral electron pair geometry, square planar molecular geometry. And the reason why this molecule is nonpolar is because you have these electronegative groups pulling the dipole moments in 4 different directions, like on a compass, north, south, west, and east. All of these dipole moments are of equal force, and so therefore they would cancel each other out. So this is a square planar molecule, but even if it was tetrahedral, let's say if it was tetrahedral, it would still, those dipole moments would still cancel out. We have already seen some examples where the dipoles did not cancel out. So let's go on and let's talk about isomers. Your lab manual discusses that the definition of an isomer is we have something called a structural isomer, and that is that the atoms are connected differently. And then there's another type of isomer called a geometric isomer, which is when all the bonds are the same, but the shape, the three-dimensional shape is different. The locations of the atoms where they are in space. Okay, so let's go ahead and see what are some different isomers that we can draw based on the molecule C2H2Cl2. So first we're going to draw the carbon-carbon double bond in the middle. And it says we need to draw 3 isomers. So here we have 3 isomers. And what I'm going to do is I'm going to clean them up. I'm going to make sure that the atoms and bond lengths are all the same. And I'm going to show all of the hydrogens like that. So now we have 3 molecules, they're all the same. And I'm going to make sure that they're all lined up to make it more nice to look at. And now we're trying to build C2H2Cl2. So where can we put the chlorines so that we have different isomers? Okay, and we are going to have 1 pair of what are called structural isomers. So if we put the 2 chlorines on one side or the other, this molecule, if we were to flip it, the chlorines would still be on the same, bonded to the same carbon. And then we have what are called cis and trans isomers. And your lab manual talks about this. These have different names. You're not going to like know these names. So the names would be something like this. And these numbers refer to which carbon are the chlorines bonded to. So in this one, this would be an example of structural isomers because 1,1-dichloroethene and 1,2-dichloroethene are going to be structural isomers because the bonds, the way that the atoms are bonded, or to which atom are the atoms bonded, are different. And then over here on the right-hand side, we have what are called geometric isomers. We say that these 2 are the cis isomers and these 2 are the trans. And what that refers to is the chlorines are on the same side of the molecule in the cis isomer, and the chlorines are on opposite sides, kind of forming like this zigzag in the trans isomer. And we can take a look at the we can take a look at what these molecules would look like in 3D if we grab them, copy to 3D. So in the 3D mode, what we can do is we can look at the molecules like so. So what we're seeing here, this is our 1,1 dichloroethene, because both of the chlorines are bonded to the carbon number 1. This would be our 1,2. Each of these would be called our 1,2 dichloroethene because the chlorines are bonded to carbons 1 and 2. And then this one here with the chlorines like opposite of each other, that would be our trans isomer. And with the chlorines on the same side, that would be our cis isomer. Oftentimes we use this kind of hand gesture. So let me just make sure that we've answered all the questions here. It's saying draw the Lewis electron dot structures. Use models to deduce the shape and polarity of each isomer. Okay, so let's talk about shape then. If we think about the electron geometry, we have 3 domains. And what I mean by that is each carbon has 1, 2, 3 regions of electron density around it. A single bond to the hydrogen counts as 1 domain, and another single bond to the hydrogen, and a double bond to the carbon counts as 1 domain. So around each of these carbons, you have trigonal planar geometry. And now if we're thinking about the dipole moments, what we can do is we can represent those with the like arrows, for example. So if we think about the electronegativity difference between the elements involved in the bonds, we have to consider the CH bond first, and then the CCl bond separately. So let's look at the electronegativity difference between carbon and hydrogen. The carbon has an electronegativity of 2.6. The hydrogen has an electronegativity of 2.2. So that would give us an electronegativity difference of 0.4. And therefore, we would not consider the CH bond a polar bond. Looking at the electronegativity of chlorine and the electronegativity of carbon, that gives us an electronegativity difference of 0.6. And that would give us a polar bond. Now, just because the molecule has polar bonds doesn't mean that the molecule is polar. We have to look at the shape. And in this case, which isomer are we talking about? So if we look at this carbon-chlorine bond and this carbon-chlorine bond, they're pulling in a similar direction. So we would be able to say that this molecule has a net dipole moment pulling towards the chlorines and away from the hydrogens. If we look at this trans isomer, it looks like these bonds would probably cancel out. So I would say that this trans isomer probably is nonpolar because the bonds are pulling with equal force in opposite directions. And so I would say that that isomer would be nonpolar. And then similarly with the cis isomer, we have 2 dipole moments and they're pulling in a similar direction. So we could say that there is a net dipole pulling towards the 2 chlorine atoms and away from the 2 hydrogen atoms. So just to make sure we fully answered the question was saying, use models to deduce the shape and polarity of each isomer. So yeah, just make sure that you say something that these are planar molecules. You can see that when you turn them to the side, you can see that they're completely flat. And that's why we call this trivial planar. Okay, let's talk about number 4. This one is saying, draw the electron dot structures for the isomers of C2H3Br3. Okay, so what we want to do is draw a carbon-carbon and another carbon-carbon. So it just has 2 isomers. And then we want to add our bromine atoms. So we're going to add 1, 2, 3 bromines, and then maybe 2 and 1 over here. Okay, so what I'm going to do is grab a lasso and clean the structure. And then I'm going to also add the hydrogens, and then I'm going to also add the carbons. So show all the carbons and make all the bonds like a nice similar size. Okay, so let me take this molecule and just scooch it over and cross them. We have 2 central atoms now. Each just kind of trying to make them look a little bit similar. Anyway, we're going to have to do a 3D optimization. So let's 3D optimize. And it's asking, do we want to remove the hydrogens? I said no. Let's do the same for this one. Let's 3D optimize. You can check these out in 3D viewer. Right, so now we're looking at the 2 isomers for C2H3Br3. The one on the left, we have all 3 bromines connected to carbon number 1. And in this case, we have 2 bromines connected to carbon number 1 and 1 bromine connected to bromine number 2. So if we were going to name these molecules, we would name them differently. So we would say that we would say that the one on the left, we would call it 1,1,1 tribromo. And then the one on the right, we would call it 1,1,2 tribromo. So by this name, we are going to be able to understand that these are structural isomers because the way the atoms are connected is different. And we are going to take a look at what is the question asking. It's saying draw the electron dot structures for 2 isomers. Are there any other isomers possible? So let's just grab these molecules and kind of give them a little spin and see if we can think about that question. So are there any other isomers possible? We don't really have, in this case, any option of cis and trans isomers because, as we talked about in an earlier video, these are all single bonds. And single bonds are able to have free rotation. So the reason why we were able to have more isomers for the Fe isomers is because they had a rigid double bond in the middle of the molecule. These molecules are able to rotate. The substituted groups are able to rotate around their carbon-carbon single bond in the middle there. So I'm not sure there are any other isomers, because if we rotate this way, then the bromines are still all bonded to the same carbon. And in this case, whether we have two on the right or whether we have two on the left, there's still only these two arrangements possible. So I don't know, you can write whatever you like for that question. I'm interested to know your wording and your thoughts. But yeah, this would be a three-dimensional representation of these two isomers. So make sure that when you're doing your base structures, make sure that you're showing all of the proper number of electrons. I didn't show the electrons, the unshared pairs on the chlorine atoms, and here I'm not showing the unshared pairs on the bromine atoms. I'm only showing the bonds. So make sure you go back and show the correct number of electrons. All right, let's do number 5, and let's start to talk about how does whether a molecule is polar or nonpolar, how does that affect the properties of the molecule? So let's go ahead and build out this molecule, propylamine. So there are some nice tools for building hydrocarbon chains. And then let's stick an amine, just one on the end of the molecule. And let's go ahead and clean it up. And let's show all of the hydrogens. And let's also show all of the carbons. And let's make all the atoms the same size. And let's make all the bonds the same length. So here we have a representation of propylamine. It has 3 carbons in its backbone, and then it has a nitrogen. And then it's suggesting that we consider another arrangement of these same atoms. So what we can do is we can generate the molecular formula for this compound, and then we can build out the other isomer, this structural isomer, where the nitrogen is the central atom. And then we have 3 CH3 groups bonded to that. So let me do the same thing. Let me clean this molecule. And show the hydrogens. Show the carbons. And make the bonds all the same length. Okay, so now we have this molecule here. The other thing that I'm not showing is the lone pair on the nitrogen. So this nitrogen has a lone pair, and this one does as well. If we were to calculate the molecular formula for this molecule, it's exactly the same. So you can see how each of these molecules is C3H9N. And we can talk about their names if we'd like to just write their names here. So the molecule on the left is called propyl, and the molecule on the right is called trimethyl. Okay, so what is it we need to understand about these two compounds? We are meant to think about the boiling points. So it says here the boiling point on this compound is 48 degrees. And the boiling point of this compound is 3 degrees. What can account for this difference? So what we're meant to think about is we're meant to think about the intermolecular forces present. And we haven't talked about intermolecular forces, but the lab manual does go over this in table 10.2. So it says that if you have a polar molecule, then you have permanent dipole-dipole forces. And that is a strong strength of intermolecular force. If you have molecules that contain H bonded to N, H bonded to O, H bonded to F, then those molecules are able to undergo hydrogen bonding. And actually, we do have an example of that in our propylamine. We have two NH bonds, and those would be able to undergo hydrogen bonding. So when a molecule is able to undergo hydrogen bonding, that is going to hold it in the liquid phase. Liquids are held together with these intermolecular forces. If you have stronger intermolecular forces, that's going to require more energy to vaporize or evaporate. So the boiling point of the propylamine is greater because of the hydrogen bonding present. The molecule on the right is not able to have hydrogen bonding. Every molecule has what are called London dispersion forces. London dispersion forces are weaker. And molecules that have London dispersion forces only tend to be more volatile, tend to be have a lower boiling point, tend to have a higher vapor pressure, and your lab manual says this. So as the strength of the intermolecular forces increases, so does the boiling point. Okay, and that brings us to our last question here of the lab. And that question is, let's talk about dimethyl ether and ethyl alcohol. So let's build out the structures for those molecules. Dimethyl ether is going to look like this, and ethyl alcohol is going to look like this. Select the molecules. Let's show all the hydrogens. Let's show all the carbons. Let's make all the atoms the same size. And the bonds all the same size. Okay. Let's move this one over. So I've just optimized for 3D. Do the same for this one. Perfect. I think you get the idea. So let's put the names on the left-hand side. We have dimethyl ethyl, and on the right-hand side, we have ethyl. And we can also calculate. I need to highlight the molecule first. Good. Calculate the molecular formula. And let's do the same with this one here. Calculate. So we can see that these are in fact also another pair of structural isomers. They have the same chemical formula, but what's bonded to what is different. For the dimethyl ether, the carbons are bonded to the oxygen, and the oxygen is the central atom. For the ethyl alcohol, the carbons are bonded to each other, and only one of the carbons is connected to the oxygen, and the oxygen is bonded to a hydrogen directly. So we can take a look at this table 10.2, which is the summary of the intermolecular forces, and we can talk about which molecule is probably going to have stronger or more impactful intermolecular forces. So if we look for which of these molecules has an H directly bonded to an O, it's only ethyl alcohol. So if we look at this one, ethyl alcohol is able to engage in hydrogen bonding, and hydrogen bonding is a strong interaction. We would say that the molecule on the left has only London forces. And the question is asking, first identify which intermolecular forces are present in each molecule. Remember that intermolecular forces are additive, so everything has London, but the hydrogen bonding is a special case of dipole-dipole. The lab manual calls it permanent dipole-dipole. Yeah. So we would say for the molecule on the right, it has all three types of intermolecular forces, and the molecule on the left has London only. And therefore, the molecule on the right, we would expect it to have a higher boiling point, we would expect it to have a lower vapor pressure, and then your lab manual talks about this principle of solubility. So for solubility, we use the rule of thumb that is called like dissolves like. And what that means is that two substances need to have a lot in common in order to be soluble. And we're asked, which one of these molecules would you imagine is expected to be more soluble in water? So if we look at the water molecule and we actually add the explicit hydrogen so that we see how it looks, we see that the water molecule has this OH group very similarly to the ethyl alcohol. So when we have a molecule that has an OH group, and it shares that OH group in common with the solvent, then these two things would mix. Whereas the dimethyl ether has what we call more hydrophobic character. When you have London forces only, that's the predominant force when you have just a hydrocarbon. And this is going to have like a lot more in common with other hydrocarbons and other hydrocarbon solvents like butane, hexane, pentane, and things that are just containing hydrocarbons. So I think that should give you enough to really get along with this experiment. And I'm really proud of you that you made it to the end of the semester in virtual instruction mode. And I want to congratulate you. If you have finished this experiment, you've finished the last experiment, experiment 10. So good job. And I'm looking forward to seeing your lab reports.